So the last thing that we had talked about in section 2.4 was we had talked about how we can write angles of any size now by embedding them inside of the xy axis. And we talked about how we can translate our right triangle definition for sine, cosine, and tangent into a point definition for sine, cosine, and tangent by viewing those, instead of relating sine, cosine, and tangent to side lengths of a right triangle, we'll relate them to the coordinates of a point on the terminal side of this angle that we embed inside of the x-axis. So let's pick up with an example there of using this information. So let's say we want to find cosine of 150 degrees. So the first thing I'm going to do is I'm going to draw myself a picture. So I'm going to draw my xy axis, and I'm going to draw a 150 degree angle. So I'm going to start by drawing the initial side of my angle, and that initial side always lies on the positive x-axis. And I'm going to rotate my other arm of the angle, the terminal side of my angle, 150 degrees. So 90 degrees to here, and then 60 more would make 150, so over around there. Everybody okay with that picture that I've drawn? What are you confused by, James? Can I help clarify? Okay.
I don't know.
So we can now draw angles of any size by embedding them inside of the xy axis. So one side of our angle, we're always going to lie on the positive side of the x-axis. We call this the initial side, that side that's always on the positive x-axis. And then we can rotate the other angle, where we're fixing one end of it at the origin, and we can rotate it around as far as we need to, as many degrees as we need to, and we can create an angle of any size. So if I rotate 150 degrees, it's going to be somewhere here in the second quadrant, because I know that between each quadrant is 90 degrees, because those are all meeting at right angles. So I did 90 degrees to pass the first quadrant, and then like 60 more lands me somewhere in that second quadrant. Okay? That's all we're saying. Okay? So if I pick a point P here on the terminal side of my angle, and I drop a perpendicular from P back down to the positive x-axis. When we draw those, we always are going to draw back down to the positive side of the x-axis. I created a right triangle. What does this angle here in my right triangle have to be? Has to be 30 degrees. Good. I know that we've gone 150, and to get to the flat line, that's 180, so I would need to go 30 more degrees to get to 180. So that angle must be 30 degrees. That means that this angle here must be 60 degrees, and what I have is a 30, 60, 90 triangle. So if I fill in my side lengths for a 30, 60, 90 triangle, I have x square root 3, x, and 2x. Everybody okay with that? So my point P has the x coordinate of well, if I started at the origin and I go to get my point, how far did I go? X square root 3. Correct with that? Everybody okay with that? Which direction did I go, though? I went to the left. So what should the sign S-I-G-N be on x square root 3? Negative. What should the y-coordinate be for my point P? X. And the sign on x should be positive, correct? Is everybody okay with that? Okay, so now if I want to evaluate cosine of 150 degrees, I can use the right triangle that I've drawn, and I can say we have adjacent over hypotenuse, which simplifies down to negative square root 3 over 2. You're welcome. Is everybody okay with that? So the one place where you might think that this is weird is that we've drawn a triangle with a negative side length on it. But we're not really drawing a side length right now. What we're doing is deciding the x-coordinate for a point on that terminal side of our angle. So it is certainly okay that we have a negative sign there. I want to make that clear, is that it looks like we're using a triangle, and in practicality we're using a kind of triangle, but it's like an imaginary triangle because we can have negative side lengths to it. Because we're not really talking about triangles, we're talking about points on the xy axis. Is everybody okay with that idea? Okay? So, as we saw today, and as we saw last time, it is possible to have values for sine, cosine, and tangent that turn out negative. We just saw a situation where we got a negative value for cosine. Under our right triangle definition for sine, cosine, and tangent, that was impossible. We might want to ask ourselves, when are those values for sine, cosine, and tangent positive or negative? Right? That's an obvious question you want to ask. And as you might have guessed, it's probably related to what quadrant the terminal side of our angle falls in. So, the first quadrant, the x's are all positive and the y's are all positive. In the second quadrant, the x's are negative, but the y's are positive. In the third quadrant, both the x's are negative and the y's are negative. And in the fourth quadrant, our x's are positive, but our y's are negative. Everybody okay with this? This is basic, like pre-algebra, just defining, using a little bit of vocab. Now, last time we met, we talked about how we can rewrite sine as y over r, cosine as x over r, and tangent as y over x, where these x and y are the point, or the coordinates of the point on our terminal side of our angle. And r, what was r again? R was a length right? It was the distance between that point and the origin. So we know that r is always positive because it's a length. In our previous picture, that's r, right? The length between, or the distance between that point P and the origin. Basically, it's the hypotenuse of our triangle, if we're drawing a triangle in there. Okay, so if I look in quadrant 1, sine is y over r, so I have a positive over a positive. Cosine, x over r, will be a positive over a positive. And tangent, which is y over x, would be positive over positive. So I know that all three of them are positive in the first quadrant. Everybody okay with that idea? If we restrict our problem down to being only a first quadrant problem, we have the trigonometry we remember from geometry. In the second quadrant, if I look at sine, which is y over r, that's positive over positive. Cosine is x over r, so I have negative over positive. And tangent, y over x, is going to be positive over negative. So both cosine and tangent are negative. I'm just going to write down the positive things in my chart here, because obviously if it's not positive there, it's negative there. So I don't need to write on both. Okay. If I move to quadrant 3, sine is negative over positive, cosine is negative over positive, and tangent is negative over negative, and I know that that makes it positive. And then into quadrant 4, sine is negative over positive, cosine is positive over positive, and tangent is negative over positive. So what I found here is that in the first quadrant, everything is positive. In the second quadrant, sine is positive, but cosine and tangent are negative. In the third quadrant, tangent is positive, but sine and cosine are negative. And in the fourth quadrant, cosine is positive, but sine and tangent are negative. The way that I remembered this is with the acronym, all silly turtles crawl. You can, well, you need something that starts with a T. So you can create your own acronym if you'd like. It can be Trevor-based if it's okay with him. Okay, good. But this is the one that I remember from high school, and it's 20 years later, and I still remember it, so it must have worked out okay for me anyways. It's silly, and it makes no sense, and it's whatever, but I remember it still, so you can use what you'd like. So next thing we're going to do is we're going to define something called a unit circle. And a unit circle is centered at the origin. And it has a radius of 1. So a tool that we're going to create for this course that we typically just call the unit circle is going to have the exact values for the angles of theta, the exact values for sine, cosine, and tangent for angles theta that we can easily calculate an exact value for. So those angles of theta that we can calculate an exact value for are multiples of 30, 45, and 60 degrees. Now, if our unit circle has radius 1, our definition for cosine of theta we said was x over r. If r is 1, cosine just becomes x, and sine becomes y. Is everybody okay with that idea? And similarly then, secant would become 1 over x, and cosecant would become 1 over y. Everybody's okay with that? All right. So what we're going to do now is we're going to use this information to record the exact values for the sine, cosine, and tangent on angles that are multiples of 30, 45, and 60. The ones that you can find exact values for, because we can use our 30, 60, 90, and 45, 45, 90 triangles onto this unit circle. So I'm giving you guys all a copy of the unit circle with everything blanked out. We'll fill this in together. Don't worry if you make a mess out of it. I've posted a blank copy on our PowerSchool page if you want to print another one out and start over again. I've also posted to the PowerSchool page one of these unit circles that's filled in, that's typed, so it's nice and neat. So you can, that's there for you as well. Everybody okay with that? All right, so let's drop this in here and we'll fill this out together. Of course. All right. So here is our blank unit circle. It's the same thing I just passed out to you guys. Let's fill this out together. Let's start by filling in the angle measures first, because that's it. We kind of need to do that first. So if we look at this spot here, what is this angle representing? 0 degrees, right? What other name could you give that, though? Could also call it 360. And then we'll fill in 90, 180, 270. Everybody okay with that? Okay. If I fill out the angles in the first quadrant, it's 30, 45, and then 60. And then I have 120, 135, 150, and then 210, 225, 240, and then I have 300, 315, and then 330. Maya? 120, 135, and 150. So again, the pattern here is the big sections are 30 degrees apart. The little sections are 15 degrees apart. So that can kind of help as well. So like this is 30, 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 So like 240 to here is 270, because I added 30. And then 270 to here is 300, adding 30. Okay with that idea? Okay. I'm going to erase those out of there, because this gets pretty busy anyways. Now I'm going to go ahead and convert each of these angle measures into radians, because oftentimes we might be asked for an angle measure in radians, and it's nice to have the radians on there as well. So 0 degrees is 0 radians. 30 degrees is pi over 6. 45 is pi over 4. 60 is pi over 3. 120 is 2 pi over 3. 135 is 3 pi over 4. And 150 is 5 pi over 6. Well, it's all also on Power School too, right? Um, 210 is 7 pi over 6. 225 is 5 pi over 4. And 240 is 4 pi over 3. Oops, I forgot 180. That's pi. And 270 is 3 pi over 2. 300 is 5 pi over 3. And 315 is 7 pi over 4. And 330 is 11 pi over 6. Correct. Eleven pi over 6 is 330. Okay. So remember that each of these points on our unit circle is in the form sine, comma, cosine. Yes, Angela? 5 pi over 3. So let's first look at, say, the 30 degree. If I want to find cosine of 30 degrees, I can use my 30, 60, 90 triangle, correct? So if I want to do cosine of 30 degrees, that's going to be the adjacent over the hypotenuse, which simplifies down to square root 3 over 2. If I want to do sine of 30 degrees, that's going to be opposite over hypotenuse, which is x over 2x, which simplifies down to 1 over 2. I'm now going to travel around the unit circle, and every place I have an angle that I make, that when I draw my perpendicular back down to the x-axis and make a 30-degree angle, I can fill in the sine and cosine values, changing the signs appropriate to the quadrant that I'm in. So if I go over to the second quadrant, if I draw a vertical or perpendicular back down to the x-axis, that would make a 30-degree angle. So this would be negative, because we're in the second quadrant, so the x's are negative, square root 3 over 2, but the y would stay positive 1/2. Next, we would go to this spot. In the third quadrant, both the x and the y are negative. And then the last spot is here. In the fourth quadrant, the x's are positive, but the y's are negative. So I filled in 4 points that basically have the same coordinate, just different coordinates are positive or negative, right? Since I've drawn my 30, 60, 90 triangle already. Let's go and work on the 60-degree angle next. So cosine of 60 would be x over 2x, or reducing down to 1/2. And sine of 60 would be opposite over hypotenuse, which simplifies down to root 3 over 2. And just like last time, I'm going to go around the unit circle, and every place where I draw a perpendicular back down to the x-axis and it makes a 60-degree angle, I'm going to fill in this same coordinate, updating the x and y being positive or negative based on the quadrant that I'm in. So the next spot is here, where the x's are positive, but the y's, the x's are negative, but the y's are positive. Then to here, where both the x and the y are negative. And last spot is here, where the x's are positive, but the y's are negative. Now let's do the 45-degree angle. Since I'm dealing with a 45-degree angle, I can calculate the sine and cosine of that using my 45, 45, 90 special triangle. So if I want cosine of 45, that's going to be adjacent over hypotenuse, which simplifies down to square root 2 over 2 if I rationalize the denominators and everything. Similarly, sine would also be square root 2 over 2. And just like I did before, I'm going to go to all those places where if I draw a perpendicular back to the x-axis, I make a 45-degree angle, and fill in those coordinates, updating them appropriately for the quadrant that we're lying in. So I have negative square root 2, and then positive square root 2 in the second quadrant. In the third quadrant, I had negative square root 2, and then negative square root 2. And in the fourth quadrant, I have positive square root 2, and then negative square root 2 over 2. Sorry. Everybody okay there? That leaves us 4 spaces remaining. These are the 4 easiest spaces to do, though. Because what is this point? What's the coordinate for that? It's the point 1, 0, right? Because I know the radius is how long? The radius for this circle is 1, so I know immediately that that's just the point 1, 0. What's the next one at 90? What's that point? 0, 1. Very good. And at 180, what is it? Negative 1, 0. Very good. And at 270, what is it? 0, negative 1. Very good. So what we have now is what we'll call the unit circle. So I have a typed out version of this posted to PowerSchool that if you want to download or print off, that's fine. You can use that. And let's just kind of give you an idea of how we can use this. Sound good? So we'll do 3 examples here of just using this unit circle. So the first thing I'm going to look for is sine of 120. So I'll go back to my unit circle. I'll find my 120-degree angle spot. And I know that sine is the coordinate. So sine of 120 is just square root 3 over 2. The next problem asks for tangent of 5 pi over 4. So I go back to my unit circle. I find 5 pi over 4. And I remember that tangent was defined as y over x. So that's going to be negative square root 2 over 2 divided by negative square root 2 over 2. Which simplifies down to 1. Lastly, I want cosecant of 390. Now, 390 isn't a value on my unit circle, but it's coterminal to a value on my unit circle. So if I go 360 and then 30 degrees more, that's 390, right? So really, I just care about this 30-degree angle. I remember that cosecant is the reciprocal of sine. So I'm going to be using the reciprocal of 1/2, which simplifies to 2. So all this unit circle is a way to shortcut around from having to draw these these special right triangles in the appropriate quadrant. It's just supposed to be a shortcut. If it's not operating as a shortcut for you, just draw the angle like we did in the previous example where we drew the found cosine of 150. You can always do it that way if that makes more sense to you and it's faster for you to do it that way. That's fine. All the unit circle is it's supposed to be a shortcut from having to do that every time. But I think that having to do that every time is pretty good practice, and I think really kind of helpful and informative to you. So it's not like I'm going to ask you to memorize the unit circle or anything. Let's do one more example kind of problem here. So this problem says find the value of sine theta if cosine theta equals 5/7 and cotangent theta is less than 0. So I'm going to start by drawing myself a picture. You can see that this is often an excellent way to start most of these trigonometry problems. How many times have I said I'm going to start by drawing myself a picture? Almost all of these examples I've been doing this, right? So I know that cosine is positive in the first quadrant and the fourth quadrant. So theta could be here, or theta might be here. We're not sure which one of these two locations we should be talking about. Is everybody okay with that idea? The way I'm going to choose between them is I'm going to use this extra piece of information that we're given, that cotangent of theta is less than 0. So I know that cotangent of theta being less than 0 is the same thing if tangent of theta is less than 0, because tangent and cotangent are reciprocals. If a number is negative, its reciprocal is negative. Everybody okay with that idea? In the first quadrant, I know that tangent is positive, so I don't want that triangle. In the third quadrant, though, I know that tangent is negative, so that is the location that I want. Is everybody okay with that idea? So I'm looking at this triangle. Since I know that cosine of theta is 5/7, I know the adjacent side is 5 and the hypotenuse is 7. And since we're in the fourth quadrant, I know that the other side that corresponds to the y-coordinate, the vertical side, needs to be negative. And to find the length for that vertical side, I can just use the Pythagorean Theorem to solve. So when I do that, I get the square root of 24, which simplifies down to 2 square root 6. You guys remember how to simplify radicals? The easiest way for this one is to just think about it as the square root of 4 times the square root of 6. Because the square root of 4 is a perfect square, I can take the square root of that. It just becomes the 2. So if I want sine theta then, I want opposite over hypotenuse. And there's my answer. So this is not much different than the problems we did in the very first problem set. The only difference being that we have to now worry about whether my answer should be positive or negative by determining which quadrant my terminal side of my angle is really in. Which quadrant are we actually operating in? And that's going to be, you can figure that out from the other piece of information. Everyone okay with this? So this wraps up our chapter 2. It was a little quick, but this was a pretty good manageable chapter. So let's finish our homework set with 47 to 60.